Welcome to this explainer. Today we're going to do something really exciting. We are translating Avi Wigderson's theoretical landscape of computational complexity into a highly practical control architecture for the real world. We aren't just getting bogged down in abstract math today. Instead, we're looking at a fundamentally new way to navigate difficult problems. You see, modern complexity theory doesn't just tell us that some problems are hard. It reveals that hardness actually has a deep, underlying structure. And once we understand that structure, well, we can use it to block blind search, protect secrets, and totally guide artificial intelligence.
Here is our roadmap for today. First, P versus NP explained. Second, the hidden constraint structure. Third, randomness, privacy, and quantum. Fourth, surviving the worst case. And finally, number 5, the energetic paradigm architecture.
All right, let's dive right into section 1, P versus NP explained.
To really grasp this landscape, we've got to distinguish between P and NP. So P stands for problems that can be solved efficiently right from scratch. Think of your car's GPS finding the absolute shortest route to a destination. The computer just crunches the numbers and hands you the answer directly. Pretty straightforward, right? But NP is a completely different beast. NP represents a class of problems where finding the answer from scratch might take an astronomically long time, like longer than the lifespan of the universe. But if someone hands you a proposed solution, you can verify if it's correct incredibly fast. So the big overarching question here is, are finding an answer and verifying an answer fundamentally different things?
And this asymmetry, where finding is super hard but checking is super easy, brilliantly illustrates why this mathematical concept is so deeply human. It captures a huge part of everyday problem solving. Think about the domains you might work in or interact with. Whether you're filling out a Sudoku puzzle, proposing a brand new scientific hypothesis, crafting a complex engineering design, or formulating a tricky medical diagnosis, generating the perfect answer completely blind is incredibly messy and difficult. But recognizing a valid solution when it finally pops up? That is so much easier. In all these messy, real-world domains, verification is absolutely our most powerful tool.
Moving right along to section 2, the hidden constraint structure.
Now here is where it gets absolutely fascinating. Seemingly isolated problems are actually secretly connected through this concept called NP-completeness. It turns out that from Boolean satisfiability to graph coloring to plotting out a massive delivery schedule or even the famous traveling salesman problem, these hard problems share a hidden structure. They can all be broken down into local consistency checks. It's kind of like a giant interconnected web of constraints. NP-completeness reveals that because they share this deep topological structure, they are literally the same problem in disguise. It proves that if you can find an efficient algorithm to crack just one of them, you crack them all. No joke.
But we also have to be really careful with the temptation of approximation. You might be sitting there thinking, well, if finding the perfect answer is too hard, I'll just settle for something that's mostly right. Actually, the PCP theorem warns us that this can be a massive deceptive trap. It shows that for certain constraint problems, improving a solution just slightly beyond a random baseline guess can sometimes require the exact same NP hard computational power as finding the perfect solution. That's right, sometimes good enough doesn't save you any compute at all. It's just as computationally demanding as exact perfection.
Let's jump into section 3, randomness, privacy, and quantum.
We usually think of randomness as just metaphysical noise, right? Like flipping a coin. But complexity theory reframes this entirely. Randomness is actually observer relative. Sure, a coin flip looks random to us, but to a supercomputer with perfect physics modeling and flawless sensor data, it isn't random at all. It's totally predictable. This means what looks like true randomness can very often be manufactured from structured computational hardness. If an algorithm is just too weak to break a hard mathematical function, the output of that function is going to look perfectly random to that algorithm. Essentially, hardness becomes usable uncertainty.
And this idea of usable hardness brings us to one of the most powerful concepts in all of modern computer science, zero-knowledge proofs. Imagine needing to prove you know a huge secret without actually revealing the secret itself. Sounds like magic, doesn't it? Well, using the NP-complete problem of graph 3 coloring, a prover can commit to a hidden answer. A verifier then randomly checks just one tiny local constraint, say one edge of a graph. The prover only reveals that tiny piece. By repeating this process over and over and over, you build this overwhelming mathematical trust without ever disclosing the full picture. It's just brilliant math, allowing verification without disclosure, which, as you know, is absolutely critical today for enterprise AI, medical privacy, and national security.
Furthermore, our security guarantees are never permanently fixed. They depend entirely on the computational power of the observer.
Right now, classical cryptography relies on the fact that factoring huge numbers is just too hard for our current computers. But, theoretically, Shor's algorithm proves that a sufficiently powerful quantum computer could just breeze right through those problems. As scalable quantum hardware becomes a future reality, it proves that computational hardness shifts entirely when the observer's power changes. And that is exactly why the industry is rushing toward post-quantum cryptography, moving our secrets into new complex geometric structures like lattice-based hardness, which quantum computers currently just can't break.
Moving on to Section 4, Surviving the Worst Case.
Because here is the real secret of it all. Worst-case hardness doesn't mean every single real-world instance is impossible to solve. Real-world systems just aren't random, worst-case mathematical objects. Take biology, for example. Biological proteins fold perfectly in mere milliseconds, even though calculating all possible folds is theoretically NP hard. Why is that? Because evolution selected a very narrow family of foldable proteins shaped by survival pressure and sheer energy costs. Supply chains, legal systems, and corporate structures, they all carry an inherent structure that is heavily shaped by history and market incentives. They have this structured reality that naturally avoids the impossible regions of the search space.
And that leads us to our final section, number 5, the energetic paradigm architecture.
Now, to be absolutely clear right out of the gate, EP does not claim to mathematically solve P versus NP. No one has done that. Let's get that out of the way. Instead, what it does is provide a highly practical control architecture for when brute force fails, when discovery is incredibly expensive, and when execution has to remain completely stable under real-world constraints. EP is a complexity-aware reasoning architecture. It uses those exact forces we just talked about, cost, selection, and history, as a practical guide to navigate the messy reality that P versus NP exposes.
This framework brilliantly illustrates how all this theoretical math actually translates into concrete action. EP acts as a translation layer. It takes the abstract realization that finding an answer is harder than checking an answer, and it operationalizes it by physically separating the generation of ideas from the verification of them. It turns NP-completeness into practical constraint mapping. It takes pseudo-randomness and turns it into bounded observer models. EP is the bridge. It turns abstract computational theory into a working, breathing governance model for AI and complex systems.
So how does this actually work in the real world? Well, instead of just asking an AI to magically hallucinate the final answer to a really hard problem, EP forces intelligence through a series of rigorous checkpoints. First, it maps the constraint topology. It explicitly separates the generation of ideas from the verification of those ideas. It relies super heavily on local consistency checks, exactly like that zero-knowledge proof we discussed earlier. By reading the energy history of real systems and protecting information flow, EP builds a tight, rigorous feedback loop that verifies local constraints and eliminates unstable branches. This structure right here, this is what stops AI from just wildly guessing.
Ultimately, Wigderson's theoretical landscape proves that computational hardness is not just a roadblock. It has structure. It can block blind search, sure, or it can be used to protect vital secrets. The energetic paradigm utilizes this exact structure to navigate intelligent search across fields that desperately need it, whether we're talking about massive scientific discovery, managing autonomous AI agents, or ensuring totally stable enterprise governance. It literally takes the limits of computation and turns them into a blueprint for controlled, intelligent action. Which leaves us with a critical reflection for your own work. As you look at the incredibly complex challenges in your field, you have to ask yourself, are you still just trying to brute force the perfect answer? Or are you taking a step back, mapping the constraints, and building a system that actually verifies its way to success? Thank you so much for joining me in this explainer. Keep questioning the structure of your problems, and I'll see you next time.